As I think about all of the various scientific ideas, whether they be hypotheses, laws, or theories, and I try to gauge which one is best known among the broad popular imagination, I think I basically come down to just a few candidates. One possibility is the atomic theory of matter. It underlies so much of our present understanding of the natural world and is so important to every other idea that Feynman suggested that if all human knowledge were to be lost but just one thing, if that idea were that matter was made up of atoms moving in a void, humanity would be able to reconstruct most of its former knowledge in just a couple of 100 years, if even that long. Yet, as foundational as this theory is, I think it's one that's now taken for granted by most, and thus not really at the front of popular consciousness. Another scientific idea might be Charles Darwin's description of how the incredible diversity of species of living organisms came about on our planet through a set of processes known as evolution and natural selection. Here in the United States, this is probably among the most contentious topics of scientific inquiry in that it stands in opposition to other, less scientific explanations for that diversity. Related to those ideas is the theoretical framework of microbiology centered on the DNA molecule and its ability to encode and pass along genetic information from one generation to the next. This knowledge promises to revolutionize the world as we know it, so much so that if the 19th century is known as the century of chemistry, and the 20th century is the century of physics, there are those who suggest that the 21st century will be the century of microbiology and biochemistry, a sentiment I am in agreement with. Yet, with both of these, there is either a complexity or lack of grandness that seems to restrict much of the work that is being done to those that are already interested in science, and so they haven't really caught the public imagination in the same way, and in those few instances where they have, it is often in a negative and sometimes apocalyptic manner. In my experience, then, there is no theory that has engaged the public in the way in which one specific theory has, even as though it's only been around for about the last 70 or so years. First hinted at in the work of both a Russian meteorologist and a Catholic priest, and then given fuller life by a Russian physicist and prankster, this theory of how the universe began has made its way into almost every person's awareness of the work of science. Originally given its name as an insult, it is even now the title of a popular sitcom franchise here in the United States. In this, it is a paradox in how something so esoteric and, in some ways, so inconsequential to how human beings live their everyday lives that it's somewhat perplexing that it has become such a touchstone. In this episode of the Scientific Odyssey, we trace the development of that idea. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 44, The Big Bang Hypothesis. As we return to our main narrative this week, it's probably useful for us to spend a bit of time reviewing where we've been, as it's been a little over a month since we last considered the expanding universe. When we last looked in on the timeline, there were two parallel avenues of investigation that were coming together. On the one hand, we had the work of establishing distances to things in order to get a sense of scale both of the galaxy we live in and of the greater universe that galaxy is a part of. Progress on the former had been made by Harlow Shapley, who showed that the Milky Way was bigger than anyone had imagined it to be, and that the Sun was a long ways off from its center. The latter area of investigation was being investigated primarily by Edwin Hubble, who showed that the Andromeda Galaxy was far enough away that it had to reside outside of the Milky Way as its own sort of island universe, or independent galaxy made up of billions, if not trillions of stars. Hubble, working with Milton Hubbison, was able to extend this analysis to a number of other spiral nebulae, as they had been called, showing that they too were separate collections of stars. Hubble also built on the work of Vesto Slipher at the Lowell Observatory in Flagstaff, Arizona, to show that not only were most of these galaxies moving away from the Milky Way, but that the further away they were, the faster they were receding. More on this in a few minutes. What's very important to note here is that both men used the tools made possible by the work and insight of George Hale, whose energy and foresight made it possible to construct first the 60-inch telescope at Mount Wilson, and a few years later the 100-inch Hooker telescope in the same location. It would be these two great instruments that Shapley and Hubble would use to gather the data they needed to make their discoveries. Had Hale not had the vision of an astrophysical laboratory, complete with the largest telescopes of his time, built in the Sierra Madre Mountains of Southern California, those discoveries might well have gone unmade for decades. Just as important, however, was the discovery of the period-luminosity relationship for Cepheid variables that had been made by Henrietta Leavitt while she worked as a calculator at the Harvard College Observatory under the direction of Edward Pickering. Again, both Shapley and Hubble used her discovery to pin down the distances to globular clusters and galaxies, respectively. As we mentioned in a previous episode, Hubble was of the opinion that Leavitt deserved a Nobel Prize for her work, but as she died before the full appreciation of the importance of what she had done was shared by the scientific community as a whole, the discussion never got very far. Separate from this work was that of Albert Einstein and the other European theoretical physicists and mathematicians who were recasting humanity's understanding of space and time. As we mentioned, Einstein in 1916 had developed a fully general theory of relativity that described how matter and energy warped or curved this thing known as space-time, and that space-time told matter and energy how to move or flow. Einstein's equation could be applied locally to understand a small region of space-time around a star or a point mass, as Minkowski had done, or it could be used to describe the evolution of the universe as an entirety. In Einstein's initial consideration of this latter problem, his initial analysis gave the solution of an expanding universe, something he felt was incompatible with the astronomical observations of the time. To solve this thing that he saw as a problem, he added a cosmological constant to his equations that served to stabilize the universe that was, in a sense, an output of that equation, something that was a steady state space-time. Now, since Einstein was working in Berlin during World War I, there was a certain embargoing, if you might call it that, of his and other scientific work that was being done in Germany, and it was only through the efforts of Willem de Sitter that his papers made it to Arthur Eddington in England. Now, it would be interesting that de Sitter would provide the next solution to the equations of general relativity by proposing a space-time empty of mass to better understand the set of equations with what he thought would be the simplest of solutions. What was really interesting in these solutions is that if you took just a little bit of mass and you sprinkled it into de Sitter's model, his spacetime, that mass tended to expand outwards quite rapidly in some cases. Eddington, familiar with Slipher's paper detailing his early observations of galactic redshifts, saw that de Sitter's results were consistent with at least a bit of the observational evidence that was emerging. Additionally, as this went on, Eddington was able to gather evidence from the solar eclipse of 1919 that supported Einstein's theory of general relativity, and so, with the verification of its validity in cosmological discussions, a number of individuals, usually of a more mathematical persuasion we should say, began to consider various models of the universe by proposing different space-time configurations with different mass and energy distributions. One such individual was the Russian Alexander Friedmann, who proposed a class of solutions for Einstein's equations. One of these solutions allowed for an expanding universe that had started from a much smaller state, something Friedmann saw as being integral and thus a likely feature of the real universe his model was trying to represent. Unfortunately, while his paper was published in a major European journal, no one really noticed it other than the few other individuals who were beginning to work in cosmology. Even more unfortunately, as we discussed, Friedmann's life was cut short by pneumonia contracted likely during a balloon flight in 1925. However, as we shall see, before his untimely death, he was able to inspire a student to continue his investigations. The other person who would go on to make significant contributions in this area was Father George Lamotta. Due to his extensive travels in both Britain and the United States, Lamotta was much more aware of the state of astronomical research in the mid-1920s, and so, when he independently developed his own solution to Einstein's equation that mirrored Friedmann's, he understood that the expansion that was contained within it was physically valid and, in fact, necessary in light of the observational evidence that was being acquired. While it would take a bit of time for Lamotta's ideas to become known to the broader scientific community, something where Eddington once again served as a vital conduit, by the time they got into the broader conversation, Hubble and Humanson's results establishing the rate of expansion of the universe had been published. The two numbers designating the rate of expansion of the universe, one from Lamotta's theoretical work and the other from the best fit line on the graph of redshift velocity versus distance from the Hubble-Humason observations, were close enough that more than one astronomer wondered if the authors hadn't been in communication prior to each paper's publication. One of the important features made explicit in Lamotta's model was the idea that if the universe was expanding, it had to have expanded from something much, much smaller. He envisioned running time backwards until not only was there no space between the expanding galaxies, those collections of stars and gas being carried away from each other by the expansion of space-time, but going even further back, he saw that there would be no separation, no space between the atoms that actually made up all of matter itself. This initial state had all of the universe being inside of a sphere no larger than about 30 times the size of our sun, something he called the Primeval Atom. At the beginning of time, he said that this atom exploded outwards, the pieces becoming the first atoms that then formed stars, that then formed galaxies, and so on as the universe expanded. He likened the whole thing to the process of atomic fission. A few years later, as the data on the expanding universe became even more incontrovertible, Einstein and de Sitter would produce a model using the simplest solution to the equations of general relativity that took into account the work of Friedmann and Lamotta, one that is still taught in graduate school classes the world over. In this model, the universe expands from a single point, known as a singularity, and this point has a very large energy and infinite mass energy density, a modification of Lamotta's primeval atom that would be vital to the work going forward. This work would also be built on by contributions by the American cosmologist Albert Robinson, who along with Englishman Arthur Walker developed a number of important mathematical descriptions of space-time that made it both homogeneous and isotropic. In other words, it looked the same no matter where you observed it. Additionally, Richard Tolman would do work that further explored Friedmann's ideas of various different possible behaviors of a universe depending on the mass it began with, by showing that a closed universe, one with enough mass to slow, stop, and reverse the expansion, would have a geometry that was consistent with a four-dimensional sphere, While an open universe, one where space-time expanded forever due to not having enough mass, would have a geometry that was saddle-shaped, or at least the four-dimensional equivalent of such a figure. One thing that should be emphasized here: you really actually don't want to think of this expansion like an explosion. That's probably the biggest misconception about this whole thing. When something explodes in our world today, it's expanding into already existing space as time progresses forward. The space into which the expanding ball of, say, hot gases and, a shock wave travels is already there. In the case of the expanding universe, that's not actually what's happening. Unlike Newton's formulation of absolute space and a separate absolute time, which exists independently of everything else, Einstein's relativistic universe intertwines space-time and energy-matter. Thus, when the universe expands, it's actually space-time that's getting bigger along with the stuff that fills it. The universe doesn't quote-unquote explode into something that's already there. What it does is it actually expands or gets bigger, and as it does so, it pulls the mass and energy along with it. And this is a really huge deal. As we've discussed in a previous episode, what that means is when we observe galaxies moving away from us, what's happening is they're being pulled away from us by the expanding, stretching fabric of space-time. And this motion is in addition to any motion that those galaxies may have due to their gravitational interactions with each other. Something cosmologists have to be careful to disentangle from the larger universal expansion when they make observations and calculations. But that's not the only thing that's going on as the universe expands. And so we need to take a look at another consequence of this, as it's going to be super important to understand what's going to take place in the 40s as these ideas get further developed. To understand this next bit, we need to talk about waves a bit more than we already have in earlier episodes of the podcast. To help with this, I want you to visualize with me a couple of different types of wave behaviors that can be experienced with musical instruments. The first phenomenon is to think of a stringed instrument, say a guitar or maybe a violin. On both ends of the neck, the string is pinned down so that it more or less can't move in either of those places. And so when you pluck the string, the middle of the string goes back and forth at a certain frequency, and that creates the musical note that you hear. What you create on the neck, or the fretboard as it's sometimes called, is what we call a standing wave, with the wavelength of that standing wave being twice the length of the fretboard, because what you really have is just half a wave between each of those two stationary points. The rate at which the string vibrates, as we said, the frequency, depends on the tension in the guitar string as well as the density from which that string is made of. So, let's see if we can expand on that. Let's pretend you can do an experiment. And let's say you could stretch out the fretboard without changing the tension in the guitar string. If you could do this, the wavelength of the wave on the string would get longer, and so the frequency would get lower. You'd then perceive a lower pitched note emanating from the guitar. Now, such a method of changing notes doesn't actually exist on string instruments exactly, though you can sort of approximate it on a fretless neck, say on a violin, by sliding the point where you would place a finger on the string while playing a note and letting that slide down towards the neck at its end. What you'll notice there is the pitch of the note will get lower. Another musical instrument where you can do this much more easily, though it does it with longitudinal sound waves instead of transverse waves on a string, is either a trombone with its slide or a child's kazoo. In both cases, the musician, and maybe I should use that term loosely with the kazoo, is able to stretch out the wave by lengthening the pipe in which the sound wave is established, thus stretching the wavelength and lowering the note. So how does this relate to an expanding universe? Well, remember, what's expanding is space-time. So when the space-time expands, not only does it carry any things that have mass along with it, it stretches any waves traveling across or through it, including light waves, a bit like slowly sliding the slide on a trombone further out. So if you were to think of a point where the universe was just large enough to have a single wave of maybe blue light span it from one end to the other, As the universe expanded, the wave would get stretched until it was, say, the size of a longer wavelength of now, let's call it red light. As the universe expands, it stretches out this blue light to red light as well. Now, that may seem a little bit weird and maybe more than just a little bit esoteric right now, but it is really going to become very, very important down the road just a ways. So, what we've got is a description of the universe based on both mathematical models rooted in a physical description of the structure of the cosmos and astronomical observations of a number of galaxies that are, in a sense, acting a bit like test particles moving in a vast spacetime. Both of these approaches gave rates of expansion that are roughly similar, and the mathematical models do a pretty good job of explaining these observational results. And that's pretty cool. Now, if you have a rate of expansion and you think that the expansion started from a single point, you might be interested in figuring out how long it took to get from that point or primeval atom or whatever to a universe that's as big as the one you see today. Fantastic. But to do this, you have to make some assumptions. The reason for this is that Hubble's observational rate of expansion is the one that you might say you have for right now. The question, though, is that has that actually been the expansion rate for the entire time the universe has been expanding? We observe it to be one number today, but has it always been that number? Well, one way to try to figure this out is to look at different distances and see if there are different expansion rates. The reason you can do this, and the reason this might work, is that if you remember, when you look further out into space, you're looking further back in time, since light takes time to travel across space. Hubble and Humasson's data seem to indicate that this was in fact the case, but everyone, including Hubble and Humasson, understood that there was too much uncertainty in their observations, something we'll return to, and that kept people from being able to make that claim with a whole lot of certainty. In other words, it remained that assumption. And it was the simplest assumption to make, and it required the least number of entities or pieces to explain. Thus, it satisfied what's known as Occam's razor. And so, that's what cosmologists at least did at first. The calculation is actually a really easy one, with the age of the universe just being the inverse of what is known as the Hubble constant, h as it's called, which is the slope of the line on that graph of galactic distance on the y-axis and galactic velocity, or how far the galaxies are moving away from us, on the x-axis. When you do the math using the number Hubble came up with, you get an age of the universe that's, well, about 2 billion years old. At least that's what they came up with at the time, using the number Hubble came up with in his initial paper. Now, from one perspective, that's a really, really long time. 2 billion years. In fact, when the number was first proposed, solar astrophysicists didn't know how to get the sun to actually shine for anywhere close to that long. The problem with the number is that there was actually, though, a lot of evidence coming from the discipline of geology that was indicating that the Earth was older than that. Probably, in fact, at least twice as old as that. Well, that's awkward. How can you have an Earth that's older than the universe? And this would only get worse as time went on, as it became clear that stars, including our sun, likely shine for not just 1 million years or 1 billion years or a couple of billion years, but in many cases for 10 or more billion years. Well, of course you can't have things in the universe that are older than the universe, and so some different things were tried in looking at the expansion rate of the universe. Lamotta worked out a model where he had a cosmological constant, something he had actually never removed from his solutions for the equations of general relativity, that was just a little bit bigger than 1. And the really interesting thing about this is that this gave a universe that expanded rather quickly initially, then sort of paused for a while, and then began expanding again, something that kind of comes out of the mathematics of all of this. Eddington, on the other hand, a deeply religious man who found the idea of a universe that just sort of came into being with a jolt of energy, philosophically unaesthetic and inelegant, suggested that the universe had always existed in a steady state until fairly recently, when it had begun to expand due to a disturbance of some sort. While both ideas are reasonably clever, each in their own way, they're also pretty ad hoc. And the problem is there really isn't anything to explain why they would be more correct than the constant expansion rate models, other than their ability to account for the observations if their parameters were chosen just right. In other words, they violated Occam's razor. Not a death sentence by any means, as there's no requirement that the razor is always true, but it posed a problem nonetheless. A simpler approach to resolving the issue was to question the accuracy of Hubble's constant, and it's here that we need to take something of a digression into what are known as standard candles. So, what's a standard candle? Well, the idea comes from imagining that one could have a type of candle that could be manufactured to a standard that always gave off the exact same amount of light. Now, what I want you to do to sort of understand why this is an important idea is to imagine that you had a large field full of people, each one holding one of these candles. And you would have the idea already that the further away one of these people was from your location of observation, the dimmer their candle would look to you. And this might give you something of a qualitative sense as to who's closer and who's further away. But to make that quantitative, what you would have to do is measure the distance to at least one of the people that was nearby in order to calibrate the whole scale. So let's say that you have a meter stick and you can measure the distance to any of the people within, say, 1 meter of your location. And then you can also determine how much light you get from each of these candles. This allows you to calibrate your scale, and then by measuring the brightness of the candles for all the other people, you can figure out how far each one is away from you and sort of get a sense of their distribution around this field, which, by the way, something I should mention, of course, the field's dark, so you actually can't see the people and you can only sort of see their candles. All right, so this sounds awesome, but now let's make things just a bit more complicated. Let's say that there are a whole bunch of different types of candles and only some of them are standard. Now, to figure out the distance to some of these people in the field, you have to be hoping that they're holding a standard candle and this is important, at least one of the people with a standard candle is close enough for you to be able to measure the distance to them. All of a sudden, things just got a little bit trickier here in our thought experiment. But let's not stop there. Let's say, you're standing in one field, but nearby there's another field with people in it, except that you don't know if it's actually another field or part of your field because the darkness doesn't let you get a good sense of depth. Also, let's say that there's some patchy fog that evening that can absorb some of the light coming from the candles before it gets to you, and that patchy fog isn't evenly distributed in any way, shape, or form. Now you're beginning to see the difficulty an astronomer has in trying to determine the distance to things that are seen in the nighttime sky. So let's link our analogy up with the real practice of doing this stuff. Of course, the standard candles are going to be stars, at least at first. The first thing we want to do is link up the actual meter stick we use to measure the distances to the stars. And so that meter stick for us, that's going to be stellar parallax, the measurement of the shift of a position of a nearby star's position based on the perspective created by the motion of the Earth around the Sun. And we've talked about this in some other episodes. This is built, of course, on knowing the distance of the Earth to the Sun, something we call an astronomical unit, to pretty good accuracy. That distance can be determined a number of different ways, including, as we've mentioned previously, by observing the transit of either Venus or Mercury across the disk of the Sun from various locations on Earth and comparing the differences in those measurements. That, of course, though, requires a good measurement of the size of the Earth and accurate timing, and those are based, of course, on even more foundational measurements. Now, the difficulty with using stellar parallax is you have to be able to measure a very, very small shift in the position of a star. Your ability to do this is a function of two things. The first is your ability to resolve angles very accurately, which is something that's based on both the size of your telescope's objective element, either the lens in the front of the telescope or the mirror at the back, depending on the type of telescope you're using, and also the wavelength of light you want to observe in, with shorter or bluer wavelengths giving you better resolution. This is where bigger telescopes are good, because the more light your scope gathers, the better your resolution is. The second thing that affects your ability to resolve is what you're trying to look at that nighttime object through. For the period we're talking about here, every telescope has to look through the Earth's atmosphere, and that limits their resolution. The atmosphere refracts the incoming light based on the composition and density of the gases that make up sort of the light path through the atmosphere between where the light from, say, the star comes into the atmosphere and where the observer is located. This density is affected by temperature and thermal motion, as anyone who's ever looked out of our hot road has seen with the shimmery and wavy nature of what is being observed, as the light from something further away from you is bent or refracted as it passes through that hot air rising off the tarmac. This is why the scene from mountaintops is so much better than the scene from low elevation sites. There's just less atmosphere to look through. Additionally, if you can look out over something with a relatively steady temperature, that stabilizes what atmosphere there is even more. This is what made Mount Wilson and Mount Palomar such good sites, at least at first. They were high, and they looked out over the cold waters of the eastern Pacific Ocean. Still, though, there's a limit to the resolution that you can get with any telescope in the Earth's atmosphere, and so that creates a limit to how far out stellar parallax will work. During the period we're discussing, that was about 150 to 200 light years, which only gets you the distance to a few hundred stars. Over time, the launch of space-based observatories such as the Hipparcos telescope, the Hubble Space Telescope, and most recently, the Gaia Observatory extends this distance significantly. But those tools aren't available to the astronomers following the First World War. The next step, the first thing that we might actually call a standard candle, was Henrietta Leavitt's observations of a specific type of variable star in the Large Magellanic Cloud, taken from photographs made by Solon Bailey at Harvard's Arequipa station. As we've previously discussed, Leavitt showed that these Cepheid variables, as they are called, had a relationship between their brightness or luminosity and how rapidly they brightened and dimmed. Now, this is a really fundamental relationship, as it allows astronomers to measure one thing, the period of variability, or the time it takes for the star to go from being dim through to being bright, back to being dim again, and then knowing how much energy, on average, the star gives off. If you do this, by measuring how bright the star looks to you and doing some math, you can figure out how far the star is away. While this seems pretty straightforward, the problem is that you have to hope that there's a star or two or three, or more is even better, that's close enough for you can use the parallax system of measurement to get the distance to those as a calibration tool. In the 1910s, as the 60-inch telescope at Mount Wilson was first coming into use, this information was spotty, and so the early estimates were, a little bit iffy. But over time, and with the addition of the 100-inch Hooker telescope, there were enough measurements made to establish the distance to a few nearby Cepheid variables that Harlow Shapley was able to determine the distance to, and then he was able to look at globular clusters, find Cepheid variables there, and thus establish the location of the center of the Milky Way galaxy and get an estimate of the size of that galaxy. A few years later, of course, Edwin Hubble was able to determine the distance first to the Andromeda galaxy and then several other nearby galaxies in addition to that using the same method. Throughout the 20s and into the 30s, Hubble and Humason would use the 100-inch Hooker telescope to extend Vesto Slipher's work in order to come up with the Hubble relationship. The thing here is that the standard candle Cepheids have a very simple limitation that they can only be used out to a distance of about, 10 million light years. Now this seems like a really enormous number, and it is, but it's only a fraction of the size of the universe. What that means is that you have to have some other types of standard candles if you want to extend your observations. The most common thing, used both by Shapley and Hubble, are what might be thought of as brightest specimen approaches. To understand this, let's take a look at what Shapley actually did with the globular clusters. When Shapley would observe a globular cluster, he would be looking for Cepheid variables to measure the period of. Now, some of the globular clusters that worked fine with, but sometimes when he looked at a cluster, he couldn't find those. And the reason you can't do that is because sometimes there's just too many stars because the clusters are so dense, and he couldn't pick out any from the background. And so he started looking for other possibilities to use as standard candles. What he realized was that in the clusters where he could see Cepheids, there were always a couple of stars that were just the absolute brightest. They sort of were brighter than everything else around them. And when he reversed the distance calculation, using the distance he calculated from the Cepheids, he found that these brightest stars always had about the same absolute brightness. They gave off the same amount of light. And so what he figured was that in a typical globular cluster, there were always going to be a few of these brightest stars that would have the same maximum brightness. So in clusters where he couldn't find Cepheid variables, he went looking for the brightest stars he could find and assumed those had the same brightness as the ones he had seen in the clusters where he was able to determine the distance to them. He then used that absolute brightness in his distance calculations. Hubble would do the same thing with galaxies that were further and further away. Now, once you get to the point where you can't resolve individual stars anymore, then what do you do? Well, you then sort of follow the same averaging techniques, but now you do it with either entire stellar clusters or with the brightest galaxies in a cluster of galaxies. In addition to this, Hubble was also able to observe nova and supernova, and he assumed that they would have a standard brightness curve. Especially, he found out, the supernova known as Type 1a supernova. And so, if he managed to spot one of these occurring in a galaxy, he could use that as a sort of standard candle. This whole thing, where one type of measurement rests on an earlier measurement, is known as the cosmic distance ladder, or cosmic distance scale. And I think there are two observations, or sort of insights, that can be made about it. First, I think it's absolutely ingenious. The men and women who contributed to its development were and are just so amazingly clever. Over the years, a number of other rings have been added to this cosmic distance ladder, including using things like the brightness of planetary nebulae, the brightness and rotation rate of spiral galaxies, and all kinds of other methods that are more technical than we have time to get into right now. These have been developed with the specific intention to overlap distance and thus cross-check against other methods in order to reduce the inherent uncertainty of each method individually. And this brings us to the second point. In each step of the ladder, there's really a compounding of uncertainties. First, you have the uncertainties inherent in the previous step, maybe the uncertainty of determination of a parallax angle used to measure the distance to a Cepheid variable. And then you also have the uncertainties in measuring the phenomenon itself. In our example here, the period of that single Cepheid variable. On top of that, you have the uncertainties in establishing the method itself, i.e. how much uncertainty is there in Leavitt's relationship. At each step, these can compound, which means it's super important to pin down what you can with as much accuracy and precision as you can. Thus, determining the distance from the Earth to the Sun to a very high degree of precision is really important. Taking lots of measurements to any given star to establish its parallax shift and thus its distance is also very important, especially if that star is a Cepheid variable. Now, alongside all of this is another line of investigation that yields really important results for determining the physical properties of stars. And this has to do with the study of the spectra they'll produce. Now, I'll have an episode on the historical developments related to determining the life cycles of stars before this series is complete. In fact, I think I'm going to do it next week. But as a part of the research that led to that, men like George Hale and women like Cecilia Payne were instrumental in determining how various physical processes produced spectral features both on the surface of the Sun and in light from other stars. This would lead to a process or a method known as spectroscopic parallax, where an astrophysicist could take a spectrum from a star and from it determine a whole host of physical characteristics for the star, including its surface temperature, its mass, its rotation rate, and most importantly for our story here, its luminosity, or how bright it was. These various relationships were calibrated using spectroscopic parallax, orbital data in the case of binary stars, and testing in Earth-bound laboratories. Now, once you have them, though, you can determine the distance to a star or a cluster of stars by getting the spectrum of them, hence spectroscopic parallax. So why is this second line of investigation so important for determining distances? Well, the reason is because it's through this means that we were finally able to determine that the space between the stars, at least inside of a galaxy, was filled with diffuse gas and dust that would absorb light and thus make the observed object look as if it were further away than it actually was. This is why we now say that Shapley's estimate of the size of the Milky Way galaxy was actually too big. He thought that the brightnesses he measured to various stars was due to the fact that he thought that all of the light could be actually reaching the observer. Now, we now know that this is not true. And the way that we know this is that when we observe the spectra of stars he measured the apparent brightnesses of, we know that they should have appeared brighter than they did based on observations of the spectra of similar stars much closer to us. This absorption correction process is actually a really tricky business, as, like in our example of observing candles in a field filled with patchy fog, the amount of absorption in each direction varies depending on what we're looking through. However, if an astronomer is careful, the corrections can be determined and applied, and the results of the observations can be trusted. As we often say, while explaining the methods can make them seem pretty simple, the actual work of gathering data can be tricky and complicated, and the secret of getting excellent data is to pay rigorous attention to the details. Okay, so now that we've spent a whole bunch of time on this digression of standard candles, why is this all important? Well, the Hubble constant is based on knowing the distances to these expanding galaxies. Actually, it's based on knowing the speeds at which they are moving as well, but it turns out that while getting the spectra of ultra-distant galaxies can be very taxing and time-consuming, once they are obtained, applying the Doppler shift is actually a fairly straightforward process and not subject to the kinds of uncertainty that the distance measurements are. What this means is if the Hubble constant gives an age of the universe that is too young, you go back and start checking the accuracy of various rungs on the cosmic distance ladder. And in time, that's what will happen. But before we get there, we need to talk about a Russian immigrant whose interest in cosmology will put the expanding universe on a much more secure physical footing. In order to move forwards in our story, we need to move just a bit backwards for a moment. When George Lamotta first proposed his model of the universe that expanded from a primeval atom in the late 1920s, we still didn't have a really great idea what an atom was. His ideas were influenced by work that Rutherford's team at Cambridge was doing to try to split the first light elements, a process that would become known as fusion. But the true nature of the nucleus was unknown, as the neutron had yet to be discovered. The reason this is important is that if you're going to put forward a model like what Lamotta did, it would be nice if the model could explain why the universe looks like the way it does now. If you say that the universe started out as something really, really hot, and then you also want to be able to explain how you get a universe that seems mostly made of hydrogen and helium with just a little bit of everything else that's actually pretty cold, and also why the stuff you see is organized in the way that it is, i.e. galaxies made up of stars and certain patterns and distributions. That's a pretty tall order for a mathematical physicist who's just sort of playing around with Einstein's equations in a time when the atom is not well understood. And to give you a sense of what's going on in physics right about this period of time, at least in terms of atomic physics, Heisenberg, Schrödinger, and Dirac are just now tearing apart the semi-classical model of the atom originally developed by Bohr and Sommerfeld and replacing it with a fully quantum mechanical picture of wave functions and probability states, along with the uncertainty principle and the Copenhagen interpretation. If you're interested in learning a bit more about that, and you haven't already done so, I would recommend, when you get done with this episode, going back and listening to our second season episodes around the mathematical atom. It's there that we dig into the history of these developments pretty heavily. Now, along with those doing work at Bohr's Copenhagen Institute was a young Russian theoretical physicist by the name of George Gamow. Gamow had been a student of Alexander Friedmann's in Leningrad, which had once been called St. Petersburg, and had managed to find a way out of the Soviet Union on a research fellowship between the years of 1928 and 1931. For 2 of those years, he worked with Bohr and Sommerfeld at both Copenhagen and Göttingen, and was able to develop an explanation of a type of radioactive decay known as alpha particle decay that used the uncertainty principle in a process known as quantum tunneling. If we had some more time, I'd go into that bit in just a little more detail, but his explanation in short was that a small piece of a large nucleus had a non-zero chance of existing outside of that nucleus, and so every once in a while, that small piece, known as an alpha particle, and shown actually to be a helium nucleus, would tunnel out of the energy barrier that usually held it in place and then fly off away from the original nucleus. It was a really clever little piece of work, and it established Gamow's reputation as an insightful and sharp thinker who was not afraid to wade into some pretty imposing calculations to get at a result. In 1931, he was called back to Russia and given a position at the University of Leningrad, but he could see that his personality and independence of mind weren't going to be all that welcome in Stalin's Russia, if you get my drift. And so, in 1933, he defected while attending a conference in Brussels and eventually landed in the United States, first at George Washington University and then later at the University of Colorado. In the 1940s, Gamow became interested in looking at processes that might take place in the early universe, assuming that either the Friedmann-Lamotta or Einstein-de Sitter model was correct. And remember, he had been a student of Friedmann's, so you can bet he was pretty well versed in working with those sorts of cosmological models, and of the opinion that they were the right way forward. To understand Gamow's work here, we first have to run the model backwards, and then we go ahead and restart it and let it run forwards. So, if we run the model backwards, what we have to remember is that as the universe gets smaller, the particle density is going to increase as a function of the volume. So since the volume goes as the distance cubed, think length times width times depth, having the size of the universe means that the particle density increases by 8 times. Half the distance times half the distance times half the distance in each direction gives 1/8 the space, which increases the density by 8 times. However, since the same thing happens with the energy in the form of light, but also in terms of the wavelength of the light getting shorter by another factor of 2, and as an aside here, energy goes as the inverse of the wavelength, i.e. the shorter the wavelength of light, the greater the energy it has. This all combines to mean that the energy density in that space goes up by a factor of 16. If you continue to add this, when you shrink the universe by, say, a factor of 10, the particle density goes up by 1,000, and the energy density goes up by 2,000. And you can sort of work this backwards. At some point, you can imagine a universe so hot and so dense that the interactions between parts of matter are not dominated by gravitational forces, but they become dominated by other things. Get the universe even smaller and hotter, and soon the atoms no longer hold together. Smaller than that, and even the nuclei can't hold together. At some tiny, tiny size, the universe is nothing but super high energy photons and the most fundamental particles that make up matter. Things are too hot for the matter to coalesce into anything bigger, and so the universe, tiny as it is dominated by the light. With this in mind, Gamow, working with a graduate student by the name of Ralph Alpher, starts to work on what happens if you start with what he called this Primeval Fireball and you run the movie forward, as it were. So, to understand what's going to happen, according to Gamow and Alpher, we need to say just a few things about fundamental particle physics. We won't get too heavy into this as it's pretty heady stuff. First, when you have a lot of energy in an environment in the form of light, photons can collide and produce particles. In the reverse process, particles can collide and produce photons. This process often involves both matter and antimatter, but it can produce just matter every so often. Second, to get pieces of matter to stick together, various types of interactions have to take place. The problem is that for these interactions to hold stuff together, you can't have photons coming along that have enough energy to blow things apart when the photons get absorbed. These two processes are going to be really, really important as the universe starts to expand. So, to start out in the very, very early universe, the energy density is high enough that all matter is completely disassociated. There are only photons and fundamental subatomic pieces of matter and antimatter. And yes, antimatter is there, and I know that's weird, but that's how it is. And so, as space-time expands and the universe cools, the matter, for reasons we don't entirely understand, is preferred by 1 part in a billion over the antimatter. As the expansion progresses, the temperature of the universe drops as the energy density drops, and below a certain temperature threshold, matter-antimatter production sort of stops on a large scale, and all of the antimatter gets annihilated by colliding with matter. Now remember, since matter is being produced at a slightly higher rate, what's left over is just matter, and what those things are basically protons and neutrons along with electrons and neutrinos, along with a lot of still really, really energetic photons. Now, during this period of time, the protons have enough energy that when they collide with an electron, they can be converted with the electrons into neutrons and a tiny little particle known as a neutrino. In the reverse process, neutrons and neutrinos can interact and create protons and electrons. This whole process keeps that proton-neutron balance at about 50-50. There are the same number of protons and neutrons in this tiny superhot universe. The interesting thing, though, is that since neutrons have just a tiny little bit more mass than the protons are actually stable where neutrons aren't, at least in isolation. Additionally, this conversion back and forth can only take place on a large scale when the temperature of the universe is greater than the energy equivalent to that mass difference. When the expansion of the universe, which is continuing to cool the universe, takes the temperature below that mass difference, the collisions of the protons and electrons are no longer energetic enough to create neutrons. However, since neutrons can still collide with neutrinos and decay into electrons or protons due to their greater mass, they continue to do so until the universe cools off that extra different little bit. This shifts the proton-neutron balance from 50-50 to about 85% protons and 15% neutrons. After this, because neutrons are unstable when they're all by themselves, i.e. not in a nucleus with another particle, they convert into protons and electrons over a period of time until they can be combined with something else into a nucleus. Since it's still too hot for protons and neutrons to stick together, neutrons start converting into protons and not getting replaced. This will continue until the universe is cool enough to allow atomic nuclei to form, which, in that period of time, there's another loss of about 3% of the neutrons. This continues until the universe is cooled enough by expansion that one neutron will get pulled together with one proton by something known as the strong interaction to form an isotope known as deuterium. And in other words, deuterium here is just one proton stuck to one neutron. The important thing is that combination stabilizes those remaining neutrons and they don't decay into other stuff anymore. This then leads to an interaction chain that will eventually form helium by gobbling up some of the other free protons that are floating around in this really super hot universe, right? After this, it turns out that it's really hard to fuse things due to nuclear stability issues. And so, according to Gamow and Alpher's theoretical work, the early universe should have contained about 76% protons, or what we think of now as hydrogen nuclei, 24% helium nuclei, and a really tiny amount of the elements lithium and beryllium. At this point, still no actual atoms exist, because there's still too many really high energy photons. Every time a nucleus tries to capture an electron, a photon comes along and blasts the electron back out of the atom. And this is going to go on for a couple 100,000 years until the temperature of the universe drops below 3,000 degrees Kelvin. By this time, the universe is big enough that nuclei and electrons are a few millimeters apart, and the proton-electron interactions drop from occurring, say, trillions of times per second to just a few times per second. And like I know, this is all just the most amazing stuff. At about this time, most of the photons have wavelengths that are just too long to actually ionize the captured electron, and once a proton can hang on to its electron for just a bit, there's this process wherein the electron drops through a series of energy levels, emitting a whole cascade, we would say, of longer wavelength, lower frequency photons. These don't have enough energy to ionize other atoms, and so very quickly the universe goes from being opaque to being transparent, and the photons can now travel without interacting with the rapidly forming neutral atoms as the protons or the helium nuclei start grabbing electrons to become neutral. Now free from their atomic chains, the photons, occupying all of the wavelengths given by the black-body spectrum of the universe at that temperature that it was at when that separation just takes place, now just does what it does. The light just travels off in a straight line, with the wavelengths slowly stretching out as the universe expands. Now, what I've given you here is a qualitative, though rather heady, description of the ideas Gamow and Alpher were working with. Behind these ideas are all of the various calculations that show just how each of these processes took place based on the physics that was known and understood at that time. In fact, many of those calculations would form the heart of Alpher's 1948 PhD dissertation, as well as a paper that is probably Gamow's best-known scientific joke. Gamow was known to be a prankster, and he loved to engage his fellow scientists in his various hijinks. Recognizing that the work they were doing needed a wider audience than just Alpher's dissertation, Gamow wrote what was a similar seminal paper for the journal Physical Review. As he would write, quote, "It seemed unfair to the Greek alphabet to have a paper signed by Alpher and Gamow only. And so the name of Dr. Hans A. Bethe in absentia was inserted in preparing of the manuscript for print. Dr. Bethe, who received a copy of the manuscript, did not object." End quote. And so it was that the paper by Alpher, Bethe, and Gamow, a play on words with both the Greek alphabet and the three types of radiation known at the time, as well as its focus on the origins of the cosmos, was published on the eminently appropriate day of April 1st, 1948. In the paper, Gamow states two very fundamental postulates that were profoundly influential going forward. First, the universe existed before stars were formed, with mostly hydrogen, but also helium and a tiny bit of heavier stuff. This mix should have been fully dependent on the laws of atomic physics, and thus were able to be calculated. Secondly, as it expanded and cooled, the universe became neutral and thus transparent to the primeval fireball. In this, the spectrum of light produced by the universe at the temperature at the time of that transition would be a black-body spectrum. Thus, as the universe expanded, that black-body spectrum should cool, and the wavelength of maximum intensity for the black-body should shift to longer and longer wavelengths until, by the point in time when the paper had been published, it would be consistent with a universal temperature a few Kelvin above absolute zero. Gamow doesn't really work out all of the consequences of these ideas in the paper, but once he puts them forward there, a whole lot of physicists get intrigued by his ideas and thus are willing to help work out a lot of the details and look for evidence. There are, however, a few problems with this. First, there's the age thing that's still out there. This isn't actually a really big deal for Gamow and Alpher, in that their ideas about the expansion rate don't really require the dates to be completely perfect. But there is an issue in that the expansion rate will influence the percentages of the elements that were formed somewhat. The bigger problem with their idea, though, is that they couldn't get their calculations to produce any elements more complicated than atomic number 4. While all of the stuff that fits into that criterion, in other words, stuff that's more complicated than atomic number 4, things that astronomers call heavy elements, amounts to less than a percent of the total number of atoms in the universe, they are there, and Gamow and Alpher's work couldn't actually make them happen. And so this leads to a number of other ideas that try to explain the data that's out there. One solution put forward by Arthur Milne, whose book on the introduction to astrophysics I used in graduate school, proposed an explosion from a central source kind of an idea. In this, there was really no need for the equations of general relativity, but it also assumed that the Milky Way was at the center of the explosion and somehow ended up not moving a whole lot. This seemed pretty unlikely, and it really did violate the Copernican principle that we're not at the center of things. It also ran counter to the observations that no matter which direction astronomers looked, the universe was basically more or less the same. In other fancy-sounding words, what we said was isotropic and homogeneous. Now, this can be fixed if one assumes that the universe is isotropic, in other words, the same in every direction, but not homogeneous, same at all distance, if one says that the universe gets denser the further away it is, and the observation of homogeneity is actually due to the motion of the observer. This is something that is exactly what special relativity would predict, but it actually requires a flat spacetime, which violates the predictions of general relativity. Thus, this whole approach that Milne puts forward seems pretty unlikely given the success of general relativity in so many other experimental tests. Another solution was suggested by Fritz Zwicky, and it's what's known as the tired photon idea. In this proposal, the photon lost energy as it traveled across space, thus causing it to redden and give the observations made by Hubble. While this would explain those observations, without having to resort to an expanding universe, there was no mechanism to explain how the photon lost energy, and there was no experimental evidence from a laboratory to suggest that this sort of thing might be correct in any way, shape, or form. It turns out there actually are also some esoteric tests of the idea that can be done by looking at the characteristic brightnesses of supernova events as well as the brightness of galaxies. The expanding universe idea gives specific predictions of how those sorts of things would be changed in terms of their observations, and it does so in a way that the tired photon idea wouldn't. As you might guess, the observations that have been made are consistent with the expanding universe's predictions rather than with the tired photon idea's predictions, and thus that idea is more or less set aside. There are also some very bizarre solutions, one of which is something known as the Goodell Universe, wherein there is a solution to the equations of general relativity that have the universe rotating in some global sense around the center. And another briefly a popular approach, at least for a little while, was known as the plasma universe, where it was thought that perhaps electromagnetic forces were more important than gravitational forces, and that galaxies would be aligned due to huge electrical currents that sort of flowed through space-time. Both of these models made certain predictions regarding what would be observed, and, those predictions have been shown more or less to be false. The most serious competitor to the Primeval Fireball idea was what was known as the steady-state universe. In this case, the idea was put forward in 1948, the same year as the Primeval Fireball idea, by Fred Hoyle, Herman Bondo, and Thomas Gold, based on earlier ideas put forward by the astrophysicist James Jeans. And their idea was that matter was being created in intergalactic space at a fast enough rate to allow the universe to keep a constant density even as it expanded. Now, if this seems to be a little bit ridiculous, what you have to understand is the rate at which matter would have to be created is actually very, very small. Something on the order of one atom, one hydrogen atom specifically, per cubic meter of space per 10 billion years to allow the universe to expand as Hubble had observed and still remain locally constant. This model allowed for an explanation of the data without having to have a super dense, super hot primeval fireball, and would allow for a more or less constant universe even as it expanded, something that was philosophically more palatable for many at the time. The steady-state model made three very testable predictions that were different from what the primeval fireball model would have said. The first of these was that there would be very different galaxy counts and observations of galaxies at large distances. The second had to do with the temperature of the universe. And here we have to make another kind of short digression. Go back and remind ourselves of something we've said before. Remember, the further you go out, the further you observe, the further back in time you are observing. And so if that's the case, according to the primeval fireball, large redshift galaxies should look hotter than closer galaxies do. And this would manifest as slight deviations in Hubble's redshift distance relationship. These sorts of things would not take place with the steady-state model. Finally, in the steady-state universe, there would be no stretched-out background radiation that was left over from that initial fireball. As these two models were established as the two main alternatives, the proponents of each took to taking shots at each other, at least good-natured shots at each other in the press. With Hoyle's group in Britain and Gamow's supporters mostly being in the United States, the feud, scientific as it was, took on the character of a friendly cross-ocean rivalry. In one BBC interview, Hoyle ridiculed Gamow's idea, saying that the steady-state model, quote, replaces a hypothesis concealed in the older theories, which assume, as I have already said, that the whole of the matter in the universe was created in one quote-unquote Big Bang at a particular time in the remote past. On scientific grounds, this Big Bang hypothesis is much less palatable of the two, for it is an irrational process that cannot be described in scientific terms. End quote. In the staid and professional norms of scientific communication, this was a drop-the-mic moment where Hoyle had decided to throw down, as it were. It is also how Gamow's hypothesis was branded with the name we all know it by today, a name that nearly every cosmologist hates for the misconception it entails, and yet cannot be done away with, so ensconced is it in the public vocabulary and imagination. So, how do we get from the place where there are two competing hypotheses to where we are today, when Gamow's idea is about as universally accepted as a scientific idea can be? Well, the answer, of course, is by gathering more data. And that process is going to take about another 20 or so years and a lot of really extraordinary work. And in order to get there, we're going to have to take a detour into stellar astrophysics. As we wrap this episode up, let me give a couple of shout-outs to a few of my fellow podcasters. First, if you haven't done so, take a bit of time to check out Brian Dunning's Skeptoid podcast, as well as his Principles of Curiosity video. Brian's doing some fantastic work in applying Carl Sagan's baloney meter to any number of different topics, and I think you'll enjoy checking him out. Also, for those of you who are fans of Roman history and who might not have heard, longtime podcaster Mike Duncan has a book coming out this week. Built on research he started for his absolutely epic History of Rome podcast, Mike's The Storm Before the Storm takes the reader through the turbulent period before the rise of Julius Caesar and the First Triumvirate. I think it's an instructive period for those watching politics in the English-speaking world right now, as well as just a darn good read. I hope you'll consider picking up a copy from your favorite retailer if you haven't already done so. Finally, let me say thanks to everyone who's taken the time to post a review of the show over the last couple of weeks. It's a huge help in getting the word out about what we're doing, and I definitely saw it push us up in the rankings on the various things that do that, especially out at iTunes. If you'd like to become more engaged in what we're doing, you can join the Scientific Odyssey group out on Facebook. Just search for the podcast name there and we'll come right up. You can also follow me on Twitter. I'm at Chad Davies. If you've got feedback, you can leave us a message on the podcast webpage, thescientificodyssey.typepad.com, where we also tend to post a little bit of additional information and graphical stuff to support the podcast. Or you can email me at cldavies@mac.com. So next week, we'll take a look at the work being done to understand how stars shine and how that solved one of the big problems with Gamow's model. Until then, full sails on your journey.